So now we're on the final part of the question, part I, where we're asked to work out the collapse load W. Now, first of all, we're going to just simply um, annotate the previous collapse load. So let's just call this um, um, A1, some A2, because it's acting on the same beam, and we denote this as just B. Yep. So let's consider A1 first. Now, what you do here is that since you have many unknowns, so you have delta 1 is unknown, delta 2 unknown, beta and alpha, you want to have a relation where you have no unknowns, and in doing so you have to use similar triangles and try to get them to relate somehow. Now the main objective is to simply equate the external work done, so the load making that deflection, and the internal work done, so the moment that's making that alpha, that's the moment that's making the beam turn into alpha and beta. So first of all, let's try to simplify some of the relationships so we can have less unknowns. So here, so we have A1, so we have delta 1. So delta 1 is simply going to be equal to, so the first segment, as you can see here, is going to be equal to 2.5 theta. Now that should be 2.5 tan theta. However, we're assuming that theta is very small, so tan theta would be the same as simply theta. So 2.5 theta. Now, when doing this, you want to make a relations in terms of the hinge. So yeah, so you would concentrate on the hinges. So this is better explained in the next part. So we would want it in terms of beta. So theta 1 would be equal to so 5.5 beta. Now we can get beta is equal to 5 theta over 11 if you just rearrange. And let's get a relation in delta 2. Now bear in mind this is still for this part to be. Okay, so theta 2. So theta 2 is going to be equal to simply 3 times by delta B. 3 times by beta, sorry. So 3 beta. Now we know what beta is equal to, so that means we can have delta 2 is equal to 3 times by 5 5 theta over 11, which is simply 15 theta over 11. So now we've got a few relationships down, so we have delta in terms of theta, and we have delta 1 in terms of theta, and we have delta 2 in terms of theta. So no alpha, that's good. So now let's work out the external work. So the external work. So we have this load W making this this delta 1 occur. So external work is simply going to be the load times by the force times by the displacement. So external work is going to be equal to delta 1 times by W plus 1.5w times by delta 2. And when you add all of this together, you simply get since we know what delta 1 is and we know what delta 2 is from the previous part of the question, we can just sub them in. So delta 1 is simply going to be equal to 2.5 theta. So we have 2.5 theta times by w, and we know what theta 2 is, delta 2 is, which is 115 theta over 11 times by w, and when you collect like terms, you get 50 over 11 w theta, theta. So now we worked out what external work is, we're going to work out what internal work is. So the internal work is simply going to be MP, because a hinge is formed, times by the rotation that the beam has gone through. So as you can see, so let's look at this section. So this part has not formed a hinge, so MP, a hinge hasn't been created, so therefore there's no internal work being done here. However, a hinge has gone through here. Now we have to know how much has been rotated. So if we extend this line, since this angle is going to be 180 minus theta minus beta, this angle is going to be theta plus beta. Actually, I might denote that in a different color, so you see. This is going to be theta plus beta, and that will be the case for the next three. I might just draw it now. Okay, so since we're still just so in this case, MP has gone by theta, has traveled theta plus beta, so it's going to be MP theta plus beta, and it's going to be, and the next MP, which occurs here, it's going to has traveled the distance of beta. So MP beta. Now we've got beta back into this, so we would obviously want to remove it, but first let's simplify a bit more. So this is what the internal work is equal to, and let's do it. MP, and since we know what beta is equal to, beta is equal to 5 theta over 11, so it's going to be theta plus 5 theta over 11 MP. Now we can collect like terms, which is equal to 21 integer over 11 times by np. And now, since we've gotten the internal work and we have it in terms of only one unknown, theta, and we know what np is because we calculate in part I, we can equate internal work with external work and simply get the collapse load W. So you have 15 to 11 W theta is equal to 21 theta over 11 P. So if you rearrange that, you get W is equal to 0.42 MP. Now, for the time being, let's leave that as it is, because we have to do this for each of these different collapse mechanisms, because we will get different values of the collapse load W. Now, to know which one is the right value is the one that's the least. So at the moment, I'll just note down that A1 has a collapse load of W 0.42 MP. 0.42 MP. So we have to repeat this for the other two mechanisms. Just deleting this section here, and we simply have to do it again for the next two. By now you can probably do this yourself. Well, you can do it anyway. So now we're dealing with beam A2. Now beam A2. So, like previously, we're going to have a relationship. We're going to try to make a relationship for theta and beta. So, in this case, we have theta 2. So we only care about what's happening in the hinge. Theta 2 is going to be equal to 5 theta. And we have theta 2 is equal to 3 beta. So therefore, this implies that beta is equal to 5 over 3 alpha. No, 5 over 3 beta. And we also have beta 1 is equal to, in this section, is going to be equal to 2.5 beta. Might make this a bit smaller. So, like previously, we're going to work out the internal work and external. We will look at the external work and the external. So the external work in this case is going to be equal to, similar to what we had previously actually, it's going to be theta delta 1 times by W and delta 2 times by 1.5 W. So external work is going to be equal to W plus by delta 1 plus 1.5 W delta 2. Now we know what delta 1 and delta 2 are. So delta 1 is in this case 2.5 theta w plus 1.5 multiplied by 5, which is equal to 7.5 theta theta w. So together that's equal to 10 theta. Okay, comes out quite nicely. So we have internal work. So internal work in this case is simply going to be MP. So if you look at it, so it's going to be MP times by theta plus beta, because that's how much it's travelled, and it's going to be plus MP times by beta. Similar to the previous question, the previous part. So that's what internal work is equal to. So this is going to be equal to theta plus 2 beta, and like you know what beta is now. So beta is simply 5 over 3 theta. So I'm just going to write the final answer here because saves a bit of time. 13 theta over 3 MP. So now we've got this, since the internal work and external work have to be the same. 10 theta w is equal to 13 theta over 3 MP, and this gives an m. That means we know that the thetas cancel out. We know what MP is, but let's leave it for the time being. But so we can get W in terms of MP, so W ends up being equal to 13 over 30 MP. So just one more step, and 13 over 30 MP is simply equal to 0.43 MP. Now if you remember what I said previously, we're looking for the smallest value for MP, because at that point with the minimum load you get a hinge, which is what you want. So let's do the last bit. The last bit is a bit easier, there's less load, so we can probably work that faster. Why is black now? So let's get a relationship. So this relationship won't be too hard to do. So since there's only one deflection that we're considering, since there's one load acting at this part of the beam, so we have delta 1 is equal to 2 times by theta, and we have delta 1 is equal to 8 beta. And from this we know that beta is equal to 1 over 4 theta. Now I'm just going to probably do internal work here. Okay, so actually sorry, let's do external work first. It's probably better to do first. Actually it doesn't matter, but internal work. So in this case we have a 2.5 W load, which is causing delta 1 to occur. So it's 2.5. So the external work is equal to 2.5 delta 1 W. We know what delta 1 is, so let's sub it in, and obviously let's sub it in terms of the theta so we can eliminate it afterwards. So if I sub it in, we get 5 theta W. So yeah, the internal work. So the internal work in this case will be a bit different. So this one's be a bit longer because previously a hinge could not form in this part and this part and even this part when he was considering that side of the beam because it was the end of the beam. However, since we're considering this mechanism now, a hinge can form here and a hinge can form here because this is a rigid support, and the hinge can obviously form in between the beam. So let's look at that, and we just so that means MP is going to be traveling a distance of theta. So we have MP times by theta plus MP will also be traveling by theta plus beta plus MP will also be traveling a distance of beta. So if I remember that correctly, I have MP times by theta plus MP times by theta plus beta, and I have MP times by beta. So this is going to be equal to 2 theta plus 2 beta times by MP. Now we know what beta is. So beta in this case is going to be equal to 1 over 4 theta. So if I just plug it in, I get 5 over 2 theta MP. And like usual, we equate to 2. So 5 over 2 theta plus 6 MP is equal to 5 theta W, and this implies that W is equal to a half MP. Let's theta cancel out. So back to this. So we have B is equal to 0.5. This is a half MP. Now obviously, which one has the lowest one? It's obviously going to be this. It's obviously going to be this one that has the lowest because it's 0.42 MP. So we simply, since we know what MP is from part I, we can multiply the two together. We can multiply 0.42 by MP, and we will get the load at collapse. So looking at that, the previous part of the question, it was found that MP is equal to 43.31 kilonewtons meters. Make sure the dimensions are correct because in III we was dealing with meters, so we obviously take this unit. So that means W is equal to 0.42 times by 43. Double check. It's 43.31. Yeah. 0.31, which is equal to calculator. We get a value of 18.19 kilonewtons. And that ends this question.